Good afternoon, everybody. Now, let us start our analytic functions. Okay, this analytic function. Analytic function, or you can say it as holomorphic function. Now comes to its definition. A function f of z is said to be analytic. Is said to be analytic at a point A belongs to Z. So at a point A belongs to C. A point A belongs to C if it is differentiable, if it is differentiable at some neighborhood of A, at some neighborhood, at some neighborhood, or in short I can say neighborhood as NBD, at some neighborhood of A. Okay, so we can say, so what is the neighborhood of A? Neighborhood of A means I can say this is S of A comma epsilon. This thing contains those Z such that Z minus A is less than epsilon. Where epsilon is a very small positive number. Okay, where epsilon is a very small positive number. So we can say f of z is analytic at a point A belongs to C means A is a complex number. So f of z is said to be analytic at a point A if it is differentiable in some neighborhood of A. That means it is differentiable in S of A comma epsilon. S of A comma epsilon means this is just a open disk. This is a open disk. Center is A, whose center is A and radius is epsilon. So in this open disk, if it is differentiable, then we will say that f is said to be analytic, or f of z is said to be analytic at this point A. So this is the definition of analyticity at a point. So what is the definition of analyticity on a region? So we can say a function f is said to be analytic. Analytic is holomorphic. Okay, both the words are same, or these two words are synonyms, but I always use this name analytic instead of this holomorphic word. Okay, so a function f of z is said to be analytic on a region D, on a region D if it is analytic, if it is analytic at every point of that region, if it is analytic at every of that region. Okay, so suppose this is the region and I am saying f is analytic in this region D. We know already how we have to check f is analytic at a point. So it is a region means it has some point. So I will say f is analytic in this region D if f is analytic at every point of the region. So how many in the region at every point f is analytic, then you can say f is analytic on that region D. Okay, so this is the definition of analyticity. Uh, Also, you may note that if f is analytic, if f this if f is analytic in whole complex in whole complex number c, then it is said to be an entire function. Then f of z is said to be an entire function e to the power s or e to the power z. These things are analytic everywhere or polynomial functions e to the power s, then polynomial functions. So these things are entire functions. That means it is everywhere analytic in C. Okay. So now comes to another note. If f is analytic at a point, if f is analytic at a point A, then f is differentiable at that point A. Okay, you already know this thing from the definition of analyticity, because f of z is said to be analytic at a point A if it is differentiable on some neighborhood of A. So on some neighborhood of A means uh, itself at that point A it is differentiable. Then in some neighborhood, okay. So this if this is a point A, so neighborhood means what? Suppose this is the point A, then its neighborhood means just make a circle around it. Let this epsilon be its radius. Or suppose this is the point A, and if you will take epsilon radius, so this will be like this, and I am saying this is a open disk whose center is at A and whose radius is epsilon. This is open circle. You may say circle is one dimension concept. So this is a open disk. Okay. So f is analytic at A means it is differentiable on this open disk. So if something is differentiable on this open disk means A is inside that, so it obviously differentiable at this center A. Okay, because A is coming inside this one, and also this points are also lying inside this open disk. Okay, so you can say if f is analytic at a point A, then f is differentiable at that point, but the reverse or the converse is not true. But the converse means the reverse is not true. Reverse is not true. Means if f is differentiable at A, suppose f is differentiable at this point only at its center, then you cannot say f is analytic at A, because for analyticity at A, it should be differentiable in this whole open disk. Okay, that means you have to, along with this center, it should be differentiable on these things, on these points. Okay, along with this center, it also needs on this point. That means inside this open disk. So whatever the points present here in this open disk, it also needs to differentiate at that point also. So you can say converse is not true. Okay. So for example, suppose I will take my f of z is equal to z square, and you know z means this is x plus iy. So this is x plus iy, that means this is x square plus y square. So if I will check this thing, this f of z, this thing is differentiable at 0. This thing is differentiable at 0. Okay, this thing is this thing is differentiable at 0, but not at 0. Okay, you can check it. Then come to another thing. If f of z is analytic at a point, then f of z has its derivative of all orders. If f of z is if f of z is analytic at a point, analytic at a point, then f of z has derivatives of all orders at that point. Has derivatives of all orders at that point. Okay, that means if suppose f of I will say suppose f of z equal to e to the power x. Suppose if I will say my f of z equal to this thing, and if it is analytic at a point, then f of z has derivatives of all order. So if this is analytic at a point a, I will say, then if I will take dash z at a or f double dash z at a, then f triple dash z, then how many times you will take? That means the all order derivatives all order, that thing exists at a. Okay, so if it is analytic at a point, then derivatives of all order exist at that point. Okay. So now comes to a theorem. So the statement of the theorem. An analytic function in a region D, an analytic function, an in a region D, an analytic function in a region D with its derivative 0, its derivative with its derivatives with its derivative 0 at every point of the domain is a constant. Derivative 0 derivative 0 at every point of the domain, at every point of the domain is a constant. The statement saying an analytic function in a region D. That means a function, suppose f of z is a function, and this is a analytic function in a region D with its derivative 0. So if you take its derivative, it is 0 at every point of the domain. That means in the domain D, it is its first derivative is 0. Then we have to show that f of z is constant. So we can add this given f function f of z. This is analytic. This is analytic in a region D. This is analytic in a region D, and f dash z is equal to 0. Its derivative is 0 at every point of the domain. That means f dash z is 0 all region D. Okay, so this thing is given to you, and you have to show that f of z is a constant. This thing is C. So how we'll show this thing? Now consider f of z. Consider f of z is equal to your u of xy. It is a complex function, so it has some real part and also some imaginary part. So let the real part be u of xy and imaginary part be v of xy. So let f of z equal to u of xy plus I times v of xy, and this is analytic in that region. Then what is your f equal to this thing? What is your f dash z? This is your ux plus I vx. So if you will apply the CR equations, then ux is equal to vy, and your uh, uy equal to minus vx. So I can write this is minus uy applying CR equations. CR equation, which is your ux equal to vy and uy equal to minus vx. Okay? So your f dash z equal to this one, or you can say this one. So what you got here? It is saying that f dash z is 0. This thing is given to equal to 0. That means this thing equal to 0 and this thing equal to 0. That means all the real part and imaginary parts are 0. So write equal to uy equal to vx equal to vy. These things are 0. Ux, vx, vy, all these things are 0. So since all these things are 0, so, this implies you can say the u and v. This implies u and v are independent of x and y. These things are independent of x and y. Partial derivative with respect to x is 0. Its u's partial derivative with respect to y is 0. That means u is independent of x and y. Similarly, vx is 0, vy is 0. So v is also independent of xy. So u and v are independent of xy. U and V, all things are independent of xy. So that means if you can say so, there is a constant. This is a C, where C is a constant. Okay. U and V are independent of xy. That means U and V are constant. Independent of xy. That means U and V are constants. And the Z is constant. Okay. So now comes to another example. You just notice what is the statement saying. If f is analytic or f function which is analytic in a region D and its derivative is 0 at every point of that domain, then that is constant. So if I write another which is very similar to that one, but both are not same. Okay, so I can say the above theorem is not true if the region is not a domain. Sorry, if the domain, if the if not a region, is not a region. So if its domain is not a region, then the above theorem is not true. And you know what is the meaning of region? A region is open plus connected. Okay. So if the domain of f of z that is not a region, then the above theorem will not true. Like if I will take an example, suppose I will take my domain D equal to 1 if D is equal sorry if or for those Z such that Z minus 1 is less than 1 and this value is 2 for those Z such that Z minus 1 is Z minus 1 modulus is less than 1 and this is Z minus 1 modulus is greater than 2. So if this will be my domain, then for this domain, sorry, this is your f of Z. So this is suppose I will take f of Z equal to 1 in this on this thing, and this is 2 on this region. This is a region, this is another region, and I am saying this is my domain. So your domain is equal to those Z minus 1 modulus is less than those Z union those Z such that Z minus 1 is greater than f of Z is defined in this way. In this region, its value is 1, and on this region, its value is 2. So, what will be your f of this is your f of Z, and you just see your f dash, but whatever D domain, this is not a region. This one region actually, this is one region, but their union is not a, because this is not connected. This is not connected because suppose this is the point 1, then Z minus 1. Sorry, if I suppose this is the coordinate system. Suppose this is 1, this is 2, this is 3, minus 2, minus 3, 2, 3, then this is minus 2, minus is Z minus 1 less than Z minus 1 modulus less than 1, that means 1 is its center and 1 is its radius. So 1 is its center and 1 is its radius, and since this is an open circle, so this thing is line. Okay. Similarly, the second one is Z minus 1 modulus is greater than 2. So 1 will be its center and 2 will be its radius. So 1 will be its center, this is center, and 2 will be its radius. So here this is 3, and here this is also 3, and here this is this distance. So 2 is its radius. So here will be 2, and here will be 2. Just 2 unit from its center. So this thing will be, and as one more less than 1, that means this thing will come, and in the second this point from here, and if I show this not connected. So since this is not connected, it is not a region. So now what I will say, f of z is defined with that is a region. So this is not region. So if your f dash z is equal to 0, that domain is not a region, then f of z is not a constant. Okay, if f of z is 1 on this domain and f of z is 2 on this domain, so you cannot say f of z is a constant because for some region it values 2. So f of z is not a constant. Theorem is not true if the domain of f of z is not a so region if f dash z equal to 0 then it is region. But uh, if the domain is not a region and f dash z is equal to 0 does not imply that f of z is a that's my aim was that thing. So now comes to another problem. So write a problem. An analytic function in a region. An analytic function. An analytic function in a region is okay. So an analytic function in a region is constant modulus constant. So let f of z, which is your u of xy plus I times y, is analytic. So this thing be in a region D, and also it has constant modulus. And since it is constant modulus, f of z is f plus I times v of xy. So mod f of z is u square modulus. Sorry. Okay. So its modulus equal to this thing, which is a constant. So if this thing is a constant, plus this is another constant. So it is a constant. K equal to 6 is a constant. Okay. So its modulus is constant means u square plus v square is a constant. So if this thing is constant, then you have to say original function z is analytic. So you have to show f of z is constant. So how we will show that f of z is a constant? So here u square plus v square equal to constant. Plus equal to v with respect to x. So taking the derivatives of both sides, derivatives of both respect to x. So if I take the derivative of both sides, we will get here both u1 here function to u ux. Then derivative of v square is 2v vx and derivative of c is 0. After taking 2 1 dividing 2 on both sides, so u equal to 0. Again, similarly, I will take derivative of both sides with respect to y. both sides with respect to y. So this is 2u uy 2v vy equal to 0, which is your uy plus v times, means I'm cancelling on both sides. So this is my equation 1 and this is my equation 2. So if I apply CR equations, then what will be this one? Suppose we will write in terms of u, and you know your CR equations. CR equations are x equal to y and uy equal to minus vx. So I apply here. So this is u, I will write x. So in y, I will write here ux equal to v. Sorry, this is not vy. This is vx. Okay. So this is vx. Okay. Whatever. So here this is minus uy. In place of vx, I will add minus uy. So in place of vx, I will add minus uy. So this is minus v times uy equal to 0. So all these terms will be in uh, u, x and uy. Similarly, if I apply this CR equations, so here uy times uy, whatever the v, I will replace by u. Only its derivative. Okay. So this will be 3 times, and uy is your, this uy is your u. So I will write, or I will replace by ux, so that all the things will be in derivatives of u, ux, uy, v, ux, all these terms ux and uy form. So let this be your 3, this is your 4, and I will remove either ux or uy. Suppose this is your uy and this is your uy. I can remove, so I will multiply equation 3 with u, equation into, so u times, this is ux v uy, u times this one equal to 0 plus v times uy v times ux equal to 0. So if you will add these two things, what you will get? This will be e square ux minus uv uy plus v times, sorry, u uy v square ux, and the right will be 0. So this will, so this will be only u square v square ux, this thing equal to 0. And this, this is here, this saying this is your constant, so this is 0. Okay. So here ux must be 0. So you will get here ux must be 0. For how we just remove uy, similarly you can also remove this ux, and if you will remove this ux, then you will get your uy is 0. So I can write similarly we can get 0 So ux equal to uy equal to 0. This implies independent of x. This is independent of x and y. This implies a constant. So similarly, we can show that v constant. You can say, or you can remove this thing also. So here we did this thing, ux equal to 0, and similarly we can show that similarly that like ux equal to 0, similarly we can show that vx equal to 0. Okay, so using the CR equation, I just converted all the things of equation 1 and 2 in terms of ux. So convert this thing in terms of vx vy. So what you will get? So whatever you will get from that, you can reduce that vx equal to 0. So after showing this vx equal to 0, then you know here f dash z ux plus ivx. So all these things are 0. Theorem, we know that if f dash z is 0 on a region D, then f dash z is 0 in the above region D, because region in the given problem. So this is 0 on the above region D. Implies you can say z is a constant in that region D. Okay, proof. So if you come to problem, any analytic function f of z, any function f of z is constant. This is u plus iv. Is a constant. Constant is itself a constant function. So this is analytic. Okay, this thing is analytic, is saying, and argument of f of z is constant. What is argument of f of z? Argument of this is f of z is u plus iv. So argument of this thing means this is tan inverse of v by u. Okay, because f of z is u plus iv, so argument of f of z is tan inverse of v by u. This is constant. Argument of f of z is equal to c, where c is a constant. That this is since c is a constant, so if v by u is a constant, then how will show that this f of z, which is your u plus iv, this is a constant? So how will show this thing? So since v by u is your k, this implies your v is equal to k into u. So this implies v into x is equal to k ux. V into x means derivative of v with respect to x. So v is equal to k ux and your vy to k uy. Now eliminating k from the above equation. So if I eliminate k, so vx by ux, this thing equal to k. Similarly here vy by uy, this thing equal to k. This implies vx by ux equal to vy by uy. So if I cross multiply this thing, so I will get vx uy equal to ux vy. Okay, and Vx uy minus ux vy. This thing equal to 0. So if I use my CR equations, um, okay, now apply CR equation. Applying CR equations. So what are the CR equations? Ux equal to minus Vx. Okay. So I will apply in such a way that all the things would be in U. So if there is a Vx, so I will replace this thing by minus Uy. So this is minus Uy into Uy minus Ux into, and your Vy is your Ux. So Ux into Ux. So this is Uy square minus Uy square minus Ux square. This implies Ux square Uy square equal to 0. So what you will get here, this is a square, this is a square, and sum of two squares is 0. That means individually both are 0. That means ux square equal to 0. This implies that ux equal to 0 and uy equal to 0. So this is your uy. Okay, this is ux equal to 0 and uy equal to 0. This implies u is independent of x and y. That means u is a constant. That means u is a constant. That means u is a u is a constant. Similarly, we can show that v is a constant. Similarly, we can show v is a constant. Thus, f of z, which is your u plus iv, is a constant. Okay. So now we got, if f of z is analytic and its argument is constant, then f of z is constant. And in the first problem, if f of z is analytic and its modulus is constant, then f of z is constant. Then come to another one. If f and f of z bar, f of z whole bar, okay, are analytic in a region D, if these are analytic in a region D, these are analytic in a region D, then show that f of z is constant on that region. Then show that f of z is constant, on that region. Okay. So f of z and f of z whole bar are analytic. So let your f of z is equal to u of xy plus I times v of xy, and it is analytic. And then what is your f of z bar? So your f of z bar will be u of xy minus I times v of xy. Okay. So You can add this thing as this is the u of x comma y plus I times this is minus j of x comma y. So all these two things are analytic under region D. So since f of z is analytic, since f of z is analytic in region D, this implies you can say ux is equal to vy on uy is equal to minus vx. Again,